Hi, Assalamualaikum and Salam Sejahtera. So let's continue our lecture by chapter 1. So for today, we are going to discuss subtopic 1.3 and 1.4. So what do we have for these two subtopics? Alright, so according to the learning outcome, for subtopic 1.3, which is under electric potential, students should be able to define electric potential where the symbol is V. Alright, and this is the equation. And then students should be able to define and sketch equipotential lines and surfaces of an isolated charge and a uniform electric field. So we have two different situations for any isolated charge, also for a uniform electric field situation. Alright, the third one, students should be able to know how to use the equation of potential equals to KQ over R. So now we have two different equations of potential. Alright, so for this we are focusing on a point charge or isolated charge and a system of charges. Okay, so what is the difference here? Here we are talking about one charge only, but for this we are talking about a system involving so many charges. Alright, so how do we use the equation? Alright, for the next part, students should be able to calculate the potential difference between 2 points. So the symbol of potential difference is delta V. Before this, we are discussing about potential. Okay, we just refer to 1 point only. But to calculate the potential difference, there must be two different points. So that delta V representing the potential difference, which is equal to the difference between V final and V initial, or V2 and V1. Alright? And then for the fifth one, students should be able to deduce the change in potential energy, or the symbol is delta U. So don't be confused. V representing potential, U representing potential energy. Alright? Okay, so we need to know how to deduce the change in potential energy between 2 points in electric field. So this is the equation of delta U, which is the change in potential energy. And then the last one for subtopic 1.3, students should be able to calculate the potential energy of a system of point charges. Again, by having so many charges, how do we calculate the total of potential energy? Okay, so we need to focus on this. Alright, that is the learning outcome for subtopic 1.3. Now let's turn for the last subtopic, which is under 1.4. So what do we have here? So under subtopic 1.4, which is charge in a uniform electric field, students should be able to explain quantitatively with the aid of diagram the motion of a charge in a uniform electric field. Okay, so what happened to the charge? When the charge is moving in an area with a uniform electric field. So we need to know how to sketch a simple diagram to explain that. And then for the second one, students should be able to use the equation of E. What is E? Electric field again, for uniform electric field. And for this, remember, we are focusing on the 4 different cases. And the first one under stationary charge. The second one, charge which is moving perpendicularly to the electric field. The third one, charge which is moving parallel to the electric field. And lastly, the charge which is in dynamic equilibrium. So remember, we need to know how to sketch a simple diagram, because we need to take out the equation later based on the diagram. Okay, now let's start by subtopic 1.3, which is electric potential. So as usual, we need to know what is the definition of electric potential. Alright, so to define the electric potential, remember the symbol of potential is V. Electric potential is V equals to W over Q naught. Alright, so this is the main equation of electric potential. So how to define it? The electric potential V at a point in an electric field is defined as the work done. So W now representing the work done to bring a unit positive charge. That one is Q naught. Okay, from infinity to that point. Okay, so actually potential representing the work done in bringing okay, a particle or charges from infinity to that point. Alright, so this is the amount of charges lah. Okay, so in simple words, energy required to bring one coulomb of positive charge from infinity to that point. So we just assume that the charge now is 1 coulomb. Alright, for this. So remember, this is the definition of electric potential, which is W over Q naught. So W representing the work done, Q naught representing the positive test charge. Alright, so remember for our syllabus, and the test charge always in positive sign. Okay, sometimes the test charge it can be negative, but according to our syllabus, it always positive. Alright, and V now representing the electric potential at that point. So the electric potential at infinity is considered 0. Okay, so remember, at infinity seems like the distance is too far, alright, so that the potential just equals to 0. And electric potential is under scalar quantity. What does it mean? We are discussing about magnitude only, so we don't have any direction. So by having positive or negative values, remember it's not under direction. I just show you how large the value is. By getting positive means that the value is really large. By getting negative, showing you that the value is really small. Okay, alright, the unit of electric potential is volt, or the symbol is capital V. So 1 volt still equal to 1 joule per 1 coulomb. How do you get this? From this equation. Okay, 1 volt equals to 1 joule divided by 1 coulomb. Alright, so this is the definition of electric potential, and this is the equation that can be used in calculating the potential. V equals to KQ over R. Alright, so Q is the amount of charges, R is the separation between that point and the isolated charge, and K is our constant. Okay, so what is the value of K? 9 times 10 to the power of 9. Alright, so as reminder, under scalar quantity, we don't have any direction, so that the sign for the charge given here, it can be positive or negative, isn't it? So it must be substituted in the calculation. For example, by having a negative charge, so Q here should be negative, so that you will get negative potential. Why? Because remember, we are discussing about a scalar quantity, so that we don't have any direction. By getting negative, showing that the value is really small. Okay, so from here we may simplify that the potential, it can be positive, it can be negative. Okay, what does it mean? For example, by giving you a positive isolated charge, and there is a point which is point A nearly to the charge. Alright, so the point and the charge separated by distance R. So what is the potential at point A? Alright, the electric potential at point A at distance R from a positive isolated charge or point charge here is given by V on A equals to KQ over R, and Q given here is a positive charge, isn't it? Alright, so that you will get VA equals to positive KQ over R. See, the potential here is positive. So remember, the area surrounding any positive isolated charge, its potential also positive. And by changing the isolated charge or point charge here to be negative, to be like this. Okay, point A still the same, separated by R. Okay, so the electric potential at point A here is given as V on A equals to KQ over R, and the isolated charge given now just negative, isn't it? So we need to substitute the negative sign here, giving you negative potential here. Okay, means that the area surrounding any negative isolated charge is under negative potential. So the potential is really small compared to the first one, which is positive, because potential is under scalar product. We don't have any direction. So positive and negative showing you how large the values is actually. Alright. Okay, so how to prove that the equation is correct? For the first case now, the potential is positive. And then for the second case given here, the potential is negative. So how to prove this? Okay, let me show you. Okay, now let's start by the first case. Okay, we need to move a positive tensed charge from infinity to a point where the distance between this point and the isolated charge is r. Okay, so the electric potential V at a point in electric field is the work done to bring a unit positive charge from infinity to that point. Okay, for this situation, we are talking about the motion of our test charge from infinity here to be on this point, which is point A. Alright, okay, how to derive the equation? Okay, remember, before this, the equation of work dW equals to F dr. So R representing the displacement, so work equal to F dr. By having a little bit changes in displacement, we are talking about little bit changes in work, isn't it? Alright, so this is the basic equation of work. So according to this situation, our test charge now is a positive charge. Also the isolated charge, also positive. Positive and positive, they are repelling each other, isn't it? Alright, so to move the test charge to be nearer to the isolated charge, the external force needed here, because they are repelled to each other. So we need to apply some external force to move the test charge to be nearer to the isolated charge. So the force, external force needed here, it must be equals to the electrostatic force. So this is the electrostatic force between our test charge and isolated charge, because they are repelling to each other. So this is the amount of Fe lah. So to move this test charge to be nearer to the isolated charge, F external needed should be equal to Fe under equilibrium. Alright, so according to this situation, okay, work equal to F dr. So this is our external force applied. It must be equals to electrostatic force, which is it just in opposite directions, isn't it? That is why we got negative sign here. Alright, so at the same time, as we know, the electrostatic force equals to kq q naught over r squared. So q, capital Q here representing our isolated charge, q naught representing our test charge. Alright, r squared is the separation between these two charges. Alright, okay, so we just substitute Fe into this equation so that you will get this. Okay, before that, we need to integrate both sides of this equation. So integration of, by integrating dW, it just equals to, okay, integration of negative Fe dr. So we just substitute Fe equals to kq q naught over r squared into this equation, giving you this. So remember, k, q and q naught just a constant. So we just take out this. Means that we need to integrate 1 over r squared with respect to r. So 1 over r squared still equals to r to the power of negative 2. Okay, what does it mean? Okay, so basically we know that 1 over r squared still equals to r to the power of negative 2. They are the same, isn't it? Alright, so by having this, then we just integrate both sides. You will get work equals to negative kq q naught, just a constant here. So by integrating r to the power negative 2 with respect to r, you will get negative r to the power of negative 1, where the range now between r and infinity. R and infinity. So by substituting r and infinity into this part or equation, so that you will get this. Work equals to kq q naught over r. Alright, so from the definition before, potential equals to work done per unit test charge. Alright, so work here equals to kq q naught over r. We just substitute work into this equation so that you will get this, where q naught and q naught cancelling each other, giving you kq over r, where the potential on A now still in positive, KQ over R. So by moving a test charge from infinity to a point nearer to a positive charge, giving you a positive potential. Okay, maybe some of you just ask me how to get this thing. Alright, so remember for integration, by having r to the power of negative 2 with respect to r, so to integrate this, okay, so what happened now, we need to r negative 2 plus 1, and then this value we need to bring in front here, isn't it, giving you negative 1 r to the power of negative 1, giving you negative r to the power of negative 1, where the range still between final and initial position, which is r and infinity. So this is the way how do we get this. One more things, how do we get this? Okay, wait now. How do we get this 1 over r from this? Okay, so let me show you. Okay, so negative r to the power of negative 1 between r and infinity still equals to 1 over r negative, okay, between r and infinity, okay, still equals to negative 1 over r, r substitute here equals to r minus negative 1 over infinity. So 1 over infinity giving you 0, isn't it? So that you will get negative 1 over r. So negative 1 over r multiplied by negative, giving you positive. So this is the way lah. How do we get the final answer which is in positive? Okay, and then by doing the same thing, okay, for the negative charge, what do I mean? We just change the isolated charge to be negative. And before this, the isolated charge given is positive, isn't it? Now by changing the isolated charge to be negative, right? The point now giving now still the same, which is point A. Alright, so we just move, okay, a test charge from infinity to that point. So remember, for any area surrounding a negative isolated charge, the potential also negative. Okay, also negative. How to prove that? Still same. By using the same equation as before. Okay, but remember, the isolated charge is negative, and then the test charge is positive. So seems like, according to Mr. Coulomb before, different charges will attract each other, isn't it? So for this, we don't have to apply any external force. Okay, the work done by the electric field or by the electric force. Okay, because they will attract each other. So for this, work equal to F dr again. So by integrating both sides, you will get this. Okay, and at the same time, F equals to electrostatic force. Remember, we don't have to apply any external force because they are attract each other. Alright, so Fe equals to KQ Q naught over R squared against the force between these two charges. Alright, substitute into this equation. And then KQ naught just a constant, take out here, and then you will get 1 over R squared. 1 over R squared is equals to R to the power of negative 2. So by integrating R to the power of negative 2 with respect to R, you will get this again in between R and infinity. By doing the same thing as before, and then you will get positive 1 over R, isn't it? So positive 1 over R times, negative 1 over R. Okay, negative 1 over R. Okay, substitute into this equation, giving you negative work. Alright, so we just substitute work into the definition of potential, which is V equal to W over Q naught, so that you will get this. Again, Q naught and Q naught cancel each other, giving you V on A now equals to negative KQ over R. So see, the potential on that point is negative. Means that for any area, okay, which is nearby the negative isolated charge, the potential also negative. Okay. Okay, now let's turn to the next part. How do we use the equation in calculating the potential? Alright, so I think the example given here is quite interesting. Alright, seems like this is a pattern of our examination question. Alright, so from the equation of V equals to QQ over R, and for any point charge or a system involving many charges, how do we use the equation in calculating the potential? Okay, now please refer to example 1.3.3. Okay, by giving you two different charges now, which is Q1 and Q2, where its magnitude is positive 2 microcoulomb and negative 2 microcoulomb. So remember, micro should be 10 to the power negative 6. Alright, so Q1 located 3 centimeter from point A, while Q2 now located at 5 centimeter from point A. So they ask you to calculate the electric potential at point A. Alright, so remember, now the potential exerted on A caused by two charges, which is by Q1, also by Q2. So that we need to calculate the total potential exerted on A, which is by Q1 and Q2. So how to calculate that? Alright, so we just start the calculation. So V exerted on A equals to V on A by 1 plus V on A by 2. So this is the potential exerted on point A by charge 1, Q1, and this is the potential exerted on point A by Q2. Alright, so remember they are under scalar product, right? We don't have any direction. So by having positive and negative sign, we need to use it, okay, in substitution. So VA1 equals to K Q1 over RA1 plus K Q2 over RA2. Alright, so we may simplify the equations to be K multiplied by Q1 over RA1 plus Q2 over RA2. Okay. So remember, K just a constant, which is equals to 9 times 10 to the power of 9. So that VA equals to 9 times 10 to the power of 9 multiplied by Q1. Q1 is 2 micro. 2 micro is 2 times 10 to the power of negative 6. And then divide by RA1. RA1 is 3 centimeters. So remember, for any calculation, we need to convert it to be in meter. So equals to 3 times 10 to the power of negative 2 meters. Okay. Plus by Q2. Q2 is negative 2 micro. We need to put negative here. Alright. Under scalar. And then over the separation now is 5 centimeter. 5 centimeter is 5 times 10 to the power of negative 2. Okay, giving you the answer. Okay. I think the answer given just be like this. This is the answer getting. V on A now equals to 2.4 times 10 to the power of 5 volt. Okay, what does it mean by this answer? Okay, from the definition, potential representing the work needed in bringing a test charge from infinity to a point. Okay, means that this is the amount of work needed, okay, to move 1 coulomb positive charge from infinity to be on this point, from infinity to be here. The work done now is 2.4 exponent 5 for 1 coulomb positive test charge. Okay, so remember, by having so many charges, we need to total up all the values of potential caused by each charges. For example, for this VA1 plus VA2, by giving you the third charge will be plus by VA3 and others. Okay, so this is the way how do we calculate the potential. Okay, now how do we calculate the potential difference? By having two different position or two different point. Okay, so this is the way. Alright, so to calculate the potential difference, which is delta V, it must be between two different position or points lah. Okay, so for example, the potential difference between point A and point B, okay, which is VAB, is given by VAB equals to VB minus VA equals to work AB over Q naught. Alright, so please listen carefully. VAB means that, okay, V between A and B. V between A and B is VB minus VA. What does it mean? Okay, AB, A representing initial point or position, B representing final point or position. So for delta V, it must be V final minus V initial. Alright, for work AB, still the same, work from A to B. So A representing the initial position and B representing the final position, the work done from A to B. So V, it must be V final minus V initial. That is why the question here just in VB minus VA. Alright, so VA is the electric potential at point A, VB is the electric potential at point B, Q naught is our test charge, and WAB is the work done in bringing a test charge from point A to point B. So from this statement, we know that A now representing the initial position or point, and B now representing our final position or final point. Alright, so the main equation for this is again, so VAB equals to V final minus V initial, which is VB minus VA, equals to the work done from A to B, from initial to final, okay, over Q naught. Or we may simplify the equations to be like this: VAB equals to work AB over Q. This is small q. Small q representing our test charge. Okay, so VAB, remember, it must be VB minus VA, which is V final minus V initial. Or the equation just be like this. By rearrange the equations, you will get WAB equals QVAB. Alright, so remember, work also under scalar quantity so that we don't have any direction. Alright, so what does it mean by positive and negative work? So this is the explanation. By getting positive work, okay, means that the work done on the electric field. Okay, on the electric field, what does it mean? By the external force. We need to apply the external force. Alright, by getting negative work, okay, what does it mean? The work is done by the electric field. So the work done by the electric force means that we don't have to apply any external force. The work done by the field itself. Okay, so that is negative work. Okay, so let's discuss one example. How do we use the equation in calculating the potential difference? Alright, so let's discuss example 1.3.4. What do we have here? 2 point charges given, which is Q1 and Q2. Q1 is a positive charge while Q2 is a negative charge. Okay, they are separated by 0.100 meters. Okay, so point A is midway between them, and point B is 0.08 meters from Q1 and 0.06 meters from Q2. So the figure given already. So this is the position of Q1 and Q2, and 2 points given, which is A and B. A is the middle point between Q1 and Q2, while B just 0.08 from Q1 and 0.06 meters from Q2. So based on this, they ask you to find the electric potential exerted on A, also the electric potential exerted on B, which is by Q1 and Q2. And then they ask you to calculate the work done by the electric field on a charge of 2.5 nanocoulomb that travels from B to A. So we just put another charge here, which is our test charge. The magnitude is 2.5 nanocoulomb, and then it just moved from B towards A. So they ask you to find the work done. Alright. Okay, so let's start by the first part, which is A. How do we calculate the electric potential at point A? Alright, so according to the figure given now, this is Q1 and this is Q2. So this is the first point given here, which is A. So the separation between A and Q1 is 0.05 meters, and then the distance between A and Q2 also 0.05 meters. So they ask you to find the potential exerted on A. So remember, the potential exerted on A is by Q1 also by Q2. So V on A equals to V on A by Q1 plus V on A by Q2. Again, we just expand the question lah. So what do we have? VA1 is KQ1 over RA1 and then plus KQ2 over RA2. Okay, so K just a constant. Remember the values is 9 times 10 to the power of 9. Q1 given already, which is positive 2.4. Q2 also given, which is equals to negative 6.5 nanocoulomb. Remember, nano should be times 10 to the power of negative 9. Okay, RA1 is the separation between point A and Q1, which is 0.05 meters. Okay, already in meters, so it's quite easy for you. Also RA2. RA2, the separation is 0.05 meters. Just substitute into the equation and then you will get the answer. Okay, something is wrong here. Actually, the answer is getting should be negative 738 volt. And we just substitute all the values given here, which is K, Q1, Q2, RA1 and RA2. Then you will get the answers to be negative 7.38 volt. Okay, by doing the same thing for point B, okay, so what do we have? V on B caused by Q1, also by Q2. So V on B equals to V on B by Q1 plus V on B by Q2, which is equals to K Q1 over RB1 plus K Q2 over RB2. Okay, again, K just a constant, which is 9 times 10 to the power of 9. Q1 given is 2.4 times 10 to the power of negative 9, which is nano, okay, and the value is positive. Q2 given is 6.50 nano, again, times 10 to the power of negative 9, and the value is negative. We need to insert negative sign here. Alright, RB1. RB1 equals to 0.08 meters, while RB2 equals to 0.06 meters. So by substituting all the values into the equation, so that you will get V on B equals to negative 705 volt. So V on A just in negative values, also V on B. Alright, so that they ask you to find work. So work, okay, so we just locate another charge, which is our test charge on B, and then we just move the test charge from B towards A. So the work done from B to A, isn't it? Work done from B to A equals to QVBA. But remember, for VBA, it must be V final minus V initial. So VBA, okay, it must be VA minus VB. So remember, V final minus V initial, because we just start by point B, and then we just finish at point A, isn't it? So this is final and this is initial lah. Alright, so substitute all the values. Okay, Q is our test charge. The test charge given now, the magnitude is 2.5 nanocoulomb. Masuk ke sini. So we just insert by inserting the values. 2.5 nano equals to 10 to the power of negative 9. Alright, multiplied by VA. VA be getting before is negative 738. And then minus negative VB, which is 705 volt. So that you will get the answers to be like this. So this is the way how do we answer the question. Okay, so remember, normally the test charge always in positive. Let's say by giving you a negative test charge, so we need to put negative here lah. Okay, so it depends on the type of our test charge. But according to our syllabus, normally the test charge always in positive sign. Okay, so this is one of the example how do you use the work equation, okay, involving the potential, electric potential. Okay, now let's discuss about the equipotential lines and surfaces. Okay, what is that actually? So the electric potential can be represented graphically by drawing equipotential lines, or in 3 dimensions. We call it as equipotential surfaces. Okay, so what is that? An equipotential surface is a surface on which all points are at the same potential. So on that surface, we may say that the potential just equals to each other. Alright? And then an equipotential line is a line on which all points are at the same potential. Again, on this line, the potential just equal to each other. So the line we call it as equipotential line. Or for any surface where the potential just equal to each other, we call it as equipotential surface. Okay, no work is done when a charge moves from one point on an equipotential surface to another point on the same surface. Okay, because the potential difference equals to 0. Alright, so according to the equation given before, work equal to Q delta V. So delta V is V final minus V initial, isn't it? So when V just equal to each other, so V minus V giving you 0. So no work done. The work done equals to 0. So this thing happen on our equipotential line or surface, and no work done because there is no potential difference. An equipotential surface must be perpendicularly to the electric field at any point. Okay, what does it mean? Okay, so this is the diagram. By giving you an isolated charge, okay, our equipotential surface should be like this, just in circle. So, for example, for this surface, okay, on this surface we have two different points, which is A and B. So A and B just located on the same surface. What do I mean? The radius still the same, isn't it? So that the potential on A and the potential on B just equals to each other, because A and B just located on the same surface. We call it as equipotential surface. Compared to C, A and C. A and C just located on different surfaces, isn't it? So RA is smaller than RC. What is R? Radius of the circle lah. So in this case, potential of A is not equals to potential of C. See, this is the conclusion. V on A equals to V on B because they are located on the same surface. But VA and VB is not equal to VC. Why? Because VC just located on other surface, where the radius is different. Alright. So for this, remember. So each dotted line here or surfaces, we call it as equipotential surface. So between A and C, which V is greater? Okay, C. Now the charge given now, the isolated charge is a positive charge. So A is nearer to the positive charge. So VA is greater than VC. By changing this isolated charge to be negative, A is nearer to our negative charge. So A is more negative compared to C, isn't it? So that VA is smaller than VC. So it depends on the type of charges given actually. But for this case, A is nearer to our positive charge. So VA is greater than VC. Alright, still the same for this. By having two different plates, which is a positive and a negative plate, so this line now representing our equipotential line. So all the lines now just parallel to the plate. So A and B just located on the same line, so that VA and VB equals to each other. While C just located on another line here, so that VA and VC should be different. Because they are not on the same surface. So in this case again, A is nearer to our positive plate, so VA is more positive compared to VC, so that VA is greater than VC. Alright, so in this case, work done between A, B. So A and B just located on the same surface, so work done from A to B equals to QVAB. So VAB equals to VB minus VA, and as we know, VB and VA equals to each other because these 2 points just located on the same surface, so that VB minus VA giving you 0. By giving you 0, then the work done also equals to 0. And the dashed line represent the equipotential surface or line. So this is the equipotential surface, and this is the equipotential lines. Okay, next, let's discuss about the electric potential energy. Okay, what is that? The electric potential energy, the symbol is capital U. okay, of a charge Q at a point in an electric field is given by, so that this is the equation of electric potential energy, which is U equal to QV. Don't be confused. Capital U representing the electric potential energy, while capital V representing our potential, electric potential. So electric potential energy equals to the charge multiplied by the electric potential. Alright, so in this case, let's say there is an isolated charge and there is a test charge. So by having this situation, we may calculate the potential energy on point A here. Okay, so potential energy on point A, or electrical potential energy on point A, equals to QVA. Okay, so what is VA? VA is the potential on point A. So in this case, the potential exerted on A is by the isolated charge. And because as we know, the equation is V equals to KQ over R. So at this point, the distance or separation between the isolated charge and A is R. So we have the potential. But by this charge, which is Q located on point A, so seems like R equals to 0. When R equal to 0, V also equals to 0. So there is no potential exerted on A by the test charge. So the potential exerted on A just by our isolated charge here. Okay, that one is VA. Okay, so as we know, VA equals to KQ, the magnitude of our isolated charge over the separation, which is R. Okay, so that you will get the equation is U equals to KQQ over R. So again, small q now representing our test charge here. Q is the isolated charge here, and R is the separation between these two charges. And again, the electric potential energy also under scalar quantity, so that we don't have any direction. So by giving you any positive or negative charge, we need to substitute the sign into the equation. Okay, again, by getting positive or negative values of U, it's just showing you how large is the energy, because we don't have any direction. Alright, so under scalar quantity, the unit is joule, or capital J for its symbol, and then the sign of charges must be substituted in the calculation. Okay, remember that, because there is no direction. Okay, we need to know the value, is it larger or smaller? Alright. Okay, so you may try to answer this exercise lah. What is the potential energy of an electron that is 0.53 times 10 to the power negative 10 meters from a proton? The answer is given already. You may try to answer this question by using this equation. Okay, good luck. Try to answer this. Okay, so by asking you to calculate the potential energy, we may use this equation directly. How about the change in potential energy? Let's say by asking you to calculate the change in potential energy, so how was the equation? Alright, so let's continue by this part. Okay, the change in electric potential energy, the symbol is delta U. So delta U equals to, again, UAB. It must be between two different points, okay, which is point A and point B. So UAB equal to U final minus U initial. So U final is B and U initial is A lah. Okay, so the UAB equals to UB minus UA. So UB equals to QVB, UA equals to QVA. Alright, so we may simplify the equations to be delta U equal to QVAB. Okay, how do we get this? So remember, the equation is U equals to KQQ over R, isn't it? Let's say at point B. At point B, KQ over R representing VB. Alright, so giving you U equals to Q here, Q multiplied by the value is now still equals to VB. QVB. That one is UB. Okay, still the same for A. UA equals to QVA based on this. Alright, from the equation of potential energy before. Alright, so UAB equals to QVAB. Alright, so change in potential energy still equals to work. So that work done between AB equals to QVAB. They are the same actually. How do you get this? From the work energy theorem. The work done equals to the change in energy. So for this, we don't have any kinetic energy. What do we have? Changes in potential energy. So the work done equals to the change in potential energy. Okay, so based on that, UAB equals to WAB. So the change in potential energy equals to the work done. So the difference between electric potential energy at point A and point B, which is UAB, equals to the work done to move or bring a charge from A to B. So this is the relationship getting from the work energy theorem. Next, how do we calculate the electrical potential energy involving many charges? Alright, so for this, okay, how do we calculate the electric potential energy of a system involving so many point charges? So now let's say there are three different charges given, which is Q1, Q2, and Q3. Then how do we calculate the total potential energy? It's quite simple. First, we need to find the numbers of couples. How many couples do we have? Okay, so for example, for these three charges, the number of couple is 1, 2, 1, 3, and 2, 3. There are three couples, isn't it? 1, 2, 1, 3, and 2, 3. And then 3, 2, still the same with 2, 3, isn't it? So we just find the number of couple. 2, 3, and 3, 2 still the same. 1, 3, and 3, 1 still the same. 1, 2, and 2, 1 also the same. So we are talking about the same couple. So the number of couple here just 3 only. So that the total energy, potential energy equals to U12 plus U13 plus U23. So U12 equals to K Q1 Q2 over R12. U13 equals to K Q1 Q3 over R13. And U23 equals to K Q2 Q3 over R23. And then we just substitute all the values of Q, also the separation between them, also K, and then you may calculate the values of U. Okay, so what is the meaning of this potential energy? The electric potential energy of the system of charges is the work done to move or bring all the charges from infinity to the points where the charge are placed. Okay, now this is the position of Q1, Q2, and Q3. By calculating the total potential energy here, or total electrical potential energy, we are talking about the work done in bringing these three charges from infinity to be here on their own position. That is the meaning of the potential energy here. Okay, so again, in calculating the electrical potential energy, we need to use the sign of the charge given, either positive or negative. Again, because they are under scalar, we don't have any direction. What do we have? Just magnitude. So we need to know the value is large or small. Based on this calculation, you may know it, okay, from the value of U, which is positive or negative. Okay.